Saturn's rings look tiny compared to this planet. Imagine a planet with rings so massive they would stretch from Earth to beyond Venus. This isn't science fiction. It's J1407b, an exoplanet with rings 200 times larger than Saturn's, spanning a mind-boggling 180 million kilometers. In this cosmic exploration, we'll journey to 7 planets that break every rule in astronomy textbooks. From worlds darker than coal to planets with impossible weather patterns and atmospheric compositions that defy conventional physics, these cosmic rebels challenge everything we thought we knew. Did ancient scientists ever imagine worlds where metal flows like water or where years pass in mere hours? Prepare to have your understanding of planetary science completely transformed. The Neptunian Desert Mystery. What if planets could exist in places science says they shouldn't? Welcome to the Neptunian Desert, a cosmic no-man's land where medium-sized planets simply aren't supposed to survive. In exoplanet science, the term Neptunian Desert doesn't refer to an actual desert, but rather a peculiar gap in our planetary discoveries. It's a region extremely close to stars where Neptune-sized worlds are conspicuously absent. The physics behind this phenomenon is straightforward. When a Neptune-like planet orbits too close to its host star, the intense radiation and heat should either boil away its atmosphere, leaving just a rocky core, or prevent such a planet from forming in the first place. Think of it like trying to maintain a snowball next to a bonfire. The conditions simply don't allow for it. This is why astronomers were utterly baffled when NASA's Transiting Exoplanet Survey satellite, TESS, detected something that shouldn't exist, a Neptune-sized object sitting right in the middle of this forbidden zone. Like finding an impossible oasis in the harshest desert on Earth, this discovery challenged everything we thought we knew about planetary formation. The initial data came through as a slight, periodic dimming of the star TOI 849, located about 730 light-years away in the constellation Fornax. This dimming pattern indicated a planet passing in front of its star, blocking a tiny fraction of starlight. The light curve suggested something extraordinary, an object roughly the size of Neptune orbiting incredibly close to its star, completing a full orbit in just 18 hours. At first, the astronomers thought there must be some mistake. Perhaps their instruments were malfunctioning, or maybe they were seeing some other astronomical phenomenon mimicking a planetary transit. After all, Neptune-sized planets shouldn't survive in such hostile environments. To verify this anomalous finding, researchers turned to the High-Accuracy Radial Velocity Planet Searcher, HARPS, at the European Southern Observatory in Chile. These follow-up observations not only confirmed the existence of a planetary body, but revealed something even more surprising about its nature. The HARPS data showed that while the planet was roughly the size of Neptune, its mass was much greater, about 40 times Earth's mass, or roughly half that of Saturn. For its size, TOI 849b was extraordinarily dense, suggesting a composition unlike any planet we've seen before. Most planets with this much mass would be much larger, as they would have sufficient gravity to hold onto a substantial atmosphere of hydrogen and helium. But TOI 849b was different. It was far too small for its mass. The unusual light curve patterns revealed an object with a sharp, defined edge rather than the fuzzy boundary typical of gas giants with extensive atmospheres. This planetary anomaly raised profound questions. How could a Neptune-sized object exist in this hostile region? If it formed there, how did it survive the intense stellar radiation? And if it formed elsewhere and migrated inward, where was its atmosphere? As scientists analyzed the data, a startling conclusion emerged. TOI 849b wasn't merely defying the rules of the Neptunian desert. It was providing evidence for an entirely new category of celestial object. What they were seeing appeared to be the exposed core of a gas giant, something astronomers had theorized about, but never directly observed before. The implications were enormous. Gas giants like Jupiter and Saturn have cores buried beneath thousands of kilometers of gas, making them impossible to study directly. But here was TOI 849b, a naked planetary core laid bare for astronomical observation, offering an unprecedented opportunity to study the interior of a would-be gas giant. This discovery was equivalent to finding a geological cross-section revealing Earth's interior layers, but on a planetary scale. Further analysis suggested TOI 849 be likely formed as a gas giant originally, accumulating a massive core of rock and metal that then gather hydrogen and helium gas from the protoplanetary disk. But something catastrophic happened. Either the planet formed too late when the gas in the disk was already dissipating, or it once had an atmosphere that was violently stripped away. This stripping could have occurred through several mechanisms: gradual erosion by the star's intense radiation, a cataclysmic collision with another massive body, or migration inward from a more distant orbit where tidal forces tore away its atmosphere. What makes TOI 849b even more remarkable is its composition. Initial spectroscopic analysis suggests the core contains large amounts of heavier elements, not just rock, metal, and ice, but possibly enhanced levels of carbon, nitrogen, and oxygen. This unusual chemical signature provides vital clues about where and how the planet originally formed. The surface conditions on TOI 849b defy imagination. With no substantial atmosphere and orbiting so close to its star, surface temperatures likely exceed 1,500 degrees Celsius, hot enough to melt rock. The planet also experiences extreme tidal forces, potentially causing intense volcanic activity across its surface. The discovery of TOI 849b has profound implications for our understanding of planetary formation and evolution. It suggests that the life cycles of planets can be far more dynamic and violent than previously thought. Gas giants might not be permanent features of their solar systems, but could potentially be stripped down to their cores under the right circumstances. This finding also suggests that exposed planetary cores might be more common than we realized. We just haven't been looking for them properly. If TOI 849b is any indication, there could be a whole population of naked planetary cores orbiting close to their stars, each one offering a unique window into the internal composition of various types of planets. TOI 849b, the planet that lost its atmosphere. While astronomers have only theorized about the mysterious cores hiding inside gas giants like Jupiter and Saturn, nature has performed a cosmic autopsy for us. TOI 849b is revealing secrets about planetary anatomy that have remained hidden since our solar system formed. Standing on TOI 849b would be unlike anything we could experience anywhere in our solar system. This bizarre world has a radius 3.44 times that of Earth, making it similar in size to Neptune. But the similarities end there. With 39 times Earth's mass packed into this relatively modest volume, TOI 849b possesses a density of approximately 5.2 grams per cubic centimeter, remarkably similar to Earth's density and completely unexpected for a planet of this size. This extraordinary density creates a fascinating paradox. According to everything we understand about planetary formation, a world with this much mass should have developed into a gas giant as planets form. Those reaching about 10 Earth masses typically generate enough gravitational pull to rapidly accumulate hydrogen and helium from the surrounding protoplanetary disk. Think of it as a planetary snowball effect. Once a forming world reaches a critical mass, it should inevitably transform into something like Jupiter, with its solid core buried beneath thousands of kilometers of atmospheric gases. Yet here sits TOI 849b, a planetary core without its atmospheric overcoat, challenging our fundamental understanding of how planets evolve. The density measurements tell a compelling story. This isn't simply a rocky super-Earth that formed naturally. Its composition signature suggests we're looking at something that should have been buried deep inside a much larger world. After carefully analyzing the data and confirming their extraordinary findings, the research team realized they had made a groundbreaking discovery. As lead researcher David Armstrong put it, This is the first time that we've discovered an intact, exposed core of a gas giant around a star. This observation essentially gives astronomers their first direct look at what normally remains forever hidden beneath vast atmospheric layers. The temperatures on this exposed core reach approximately 2,780 degrees Fahrenheit, 1,530 degrees Celsius, hot enough to melt lead, zinc, and even some types of rock. These extreme conditions result from its incredibly tight orbit, completing a full circle around its star in just 18 hours. At such close proximity, the star's radiation would be overwhelming, the skies permanently ablaze with stellar energy that would make our sun appear mild by comparison. What could explain TOI 849b's unusual state? Astronomers have developed three compelling theories, each with profound implications for our understanding of planetary systems. The first possibility is that TOI 849b represents a failed gas giant. Perhaps during its formation, a gap opened in the protoplanetary disk exactly where the young planet was developing. With its gas supply cut short, the planet's core formed normally, but it never accumulated the thick atmosphere typical of worlds its size. This scenario would teach us about the delicate timing and conditions necessary for gas giants to develop fully. The second theory suggests TOI 849b once possessed a massive atmosphere, but lost it through intense stellar radiation in a process called photoevaporation. Like a cosmic blowtorch, the nearby star could have gradually stripped away the hydrogen and helium envelope, leaving only the dense core behind. This would demonstrate how vulnerable even massive planetary atmospheres can be when orbiting close to active stars. The third and perhaps most dramatic possibility involves a catastrophic collision with another planetary body, a cosmic car crash of unimaginable proportions. Such an impact could have violently ejected the atmosphere into space, leaving the mangled core as the only survivor. If this is what happened, TOI 849b bears witness to the violent nature of young planetary systems. Each explanation carries different implications for planetary science, which is why astronomers are so eager to gather more data about this strange world. The composition of any remaining atmospheric traces could help determine which scenario is most likely. Detection of certain elements would support specific formation and evolution pathways. The surface conditions on TOI 849b would be utterly alien. Without a substantial atmosphere, there's no weather as we understand it, no clouds, no wind, just the stark boundary between scorching rock and the vacuum of space. The crushing gravity, about 11 times stronger than Earth's, would flatten any hypothetical visitor instantly. The extreme pressure deep within the planet might create exotic states of matter we can't reproduce in Earth laboratories. What makes TOI 849b truly valuable to science is how it serves as a natural laboratory for studying planetary interiors. Normally, astronomers can only infer what exists at the center of gas giants through indirect measurements and models. Jupiter's core, for instance, remains mysterious despite numerous space missions. We've never seen the heart of a gas giant until now. TOI 849b allows scientists to directly observe and analyze what typically remains hidden. Its composition likely includes higher concentrations of heavy elements than would be found in the outer layers of a gas giant. By studying the spectroscopic fingerprints of any remaining atmospheric elements, astronomers can determine exactly what materials make up this exposed core. This information is crucial for improving our models of planet formation throughout the galaxy. If we understand what gas giant cores are made of and how they form, we gain insight into the processes that built our own solar system. TOI 849b essentially provides a shortcut to knowledge that would otherwise require physically boring through thousands of kilometers of Jupiter's atmosphere, an impossible task with current technology. The planet's extreme density also raises intriguing questions about the states of matter that might exist in its interior. Under such immense pressure and heat, familiar materials behave in unfamiliar ways. Metals can become liquid, or even take on properties of both liquids and solids simultaneously. TOI 849b represents an entire class of objects that astronomers haven't properly recognized until now. Its discovery suggests we should be searching for more exposed planetary cores around other stars, each potentially providing different pieces of the planetary formation puzzle. WASP 12b, the planet being eaten alive. From exposed planetary cores to cosmic cannibalism. What happens when a star begins to eat its own planet? At just 2.1 million kilometers from its host star, 1/60th of Earth's distance from the Sun, WASP 12b is experiencing the ultimate planetary nightmare, losing 6 billion metric tons of its mass every second. This doomed world was discovered in 2008 by the Wide-Angle Search for Planets project, and it didn't take long for astronomers to realize they were witnessing something extraordinary. WASP 12b orbits catastrophically close to its star, completing an entire orbit in a mere 1.1 Earth days, caught in a deadly embrace with its stellar host that will ultimately prove fatal. The proximity to its star subject's WASP 12b to gravitational forces so intense they're literally reshaping the planet. Rather than maintaining the spherical form we associate with planets, these tidal forces have stretched WASP 12b into an elongated, rugby ball-like shape. Imagine the planet's mass stretching like cosmic taffy, pulled by invisible hands, its structure warping and yielding under the relentless gravitational pull. This deformation marks a death sentence for the planet. The gravitational stretching generates tremendous friction within the planet's interior, creating what astronomers call tidal heating. This internal friction contributes to WASP 12b's inflated size and accelerates the processes leading to its ultimate destruction. The planet cooks from the inside, while simultaneously being torn apart from the outside. The surface conditions on WASP 12b defy imagination. Temperatures soar beyond 2,500 degrees Celsius, hot enough to break down most molecular bonds and turn familiar materials into exotic states of matter. At these temperatures, even rocks would exist as vapor in the atmosphere. Any spacecraft venturing too close would be vaporized instantly, its components reduced to their constituent atoms in seconds. What truly sets this world apart is that we're witnessing its active destruction in real time. Space telescopes, including Hubble and Spitzer, have observed something remarkable. The planet's atmosphere is literally escaping into space, creating an extended cloud of gas that surrounds the star. This mass loss occurs at an astonishing rate, approximately 6 billion metric tons every second. To put that in perspective, that's equivalent to losing the mass of Mount Everest every 3 minutes. Even with its substantial size, mathematics tells a clear story. At this rate of loss, WASP 12b is only a few million years left before it will be completely consumed by its star, merely an eye blink in astronomical timescales. The escaping atmosphere follows a visible stream directly toward WASP 12. Astronomers are essentially watching a cosmic feeding process as the star slowly devours its planetary companion bit by bit. WASP 12b's orbit is actively decaying. The gravitational dance between planet and star is causing WASP 12b to spiral inward through a process called tidal dissipation. Like a cosmic whirlpool, the planet is being drawn inexorably closer to its demise with each passing year. The exchange of energy between planet and star leads to a loss of angular momentum, accelerating the planet's journey towards stellar consumption. WASP 12b possesses one of the most unusual atmospheres ever discovered. Spectroscopic observations reveal an extraordinarily carbon-rich composition with significant quantities of carbon monoxide and hydrogen cyanide, making it a stark contrast to most planets in our solar system, which have more oxygen than carbon. This chemical fingerprint suggests that this world formed under conditions very different from those that created our home system's planets, expanding our understanding of how diverse planetary systems can be throughout the galaxy. Perhaps most surprising is WASP 12b's appearance. Despite its hellish conditions, if we could somehow view it directly, we wouldn't see a bright, reflective world. Instead, WASP 12b absorbs nearly all the light that reaches it, reflecting very little back into space. This extremely low albedo means that the planet appears almost black, making it one of the darkest planets ever observed. Scientists believe this darkness results from the planet's lack of significant cloud cover combined with its unique atmospheric chemistry. The same extreme heat that's tearing the planet apart prevents the formation of reflective clouds, while its carbon-rich composition further enhances its light-absorbing properties. Though WASP 12b is being destroyed in a blaze of stellar radiation, paradoxically, it appears as a dark shadow against its brilliant host star. The scientific value of observing a planet in the process of destruction cannot be overstated. WASP 12b provides astronomers with a natural laboratory for studying extreme planetary physics, atmospheric escape mechanisms, and the ultimate fate of planets that orbit too close to their stars. Every observation adds to our understanding of these processes, which may have played out countless times throughout our galaxy's history. While TOI 849b likely lost its atmosphere long ago through similar processes, WASP 12b lets us watch the destruction in progress. These observations challenge our models of planetary evolution and survival, showing that the life cycles of planets are far more diverse and dynamic than previously imagined. The WASP 12 system raises intriguing questions about planetary system architecture. How did WASP 12b end up in such a perilously close orbit? Was it formed farther out and migrated inward? The answers might help explain the prevalence of hot Jupiters throughout the galaxy and provide insights into the likelihood of Earth-like planets surviving in other systems. As our telescopes improve and our observational campaigns continue, astronomers expect to witness more of WASP 12b's death spiral. Each observation provides another snapshot in this planet's dramatic end, contributing to a time-lapse of cosmic destruction playing out over millions of years. This stellar cannibalism, while spelling doom for WASP 12b, offers an unprecedented opportunity for human knowledge. HD 189773b, where glass rain falls sideways. From a planet being devoured by its star, we shift our attention to a world whose beauty masks a deadly secret. Just 64 light-years away in the constellation Vulpecula lies HD 189733b, a hot Jupiter with a striking deep blue appearance that might momentarily fool you into thinking you're looking at a distant cousin of our own ocean-covered world. This azure exoplanet could easily be mistaken for Earth in an artist's rendering, but appearances can be dangerously deceiving. Unlike Earth, where our oceans reflect blue light back into space, HD 189733b's color comes from something far more sinister. Its atmosphere is filled with tiny silicate particles, essentially the building blocks of glass, that scatter blue light while absorbing red wavelengths. What appears as a peaceful blue marble from afar is actually a scorching inferno with weather conditions that redefine our understanding of extreme. While Earth's most violent hurricanes might reach sustained winds of 200 miles per hour, they're gentle breezes compared to what's happening on HD 189733b. This exoplanet experiences winds raging at an almost incomprehensible 5,400 miles per hour, over 8,700 kilometers per hour. These gales reach 7 times the speed of sound. Winds powerful enough to circle Earth's equator in under 5 hours demonstrate the scale of these atmospheric currents. The planet's proximity to its star creates these extraordinary conditions. HD 189733b orbits its sun at a mere 3 million miles, about 13 times closer than Mercury orbits our sun. This tight orbital dance means the planet completes a full revolution in just 2 Earth days, with one side permanently facing its star in what astronomers call tidal locking. The result is a temperature gradient that drives these ferocious winds and creates surface temperatures averaging around 1,700 degrees Fahrenheit, 926 degrees Celsius. At these temperatures, something terrifying happens to those silicate particles in the atmosphere. They melt. What begins as tiny bits of dust transforms into droplets of liquid glass. Unlike rain on Earth, which falls more or less vertically, HD 189733B's molten glass precipitation gets caught in those supersonic winds. The result is a sideways glass rainstorm traveling at hypersonic speeds across the planet's atmosphere. Imagine driving through a hailstorm where the windshield suddenly shatters into millions of razor-sharp fragments. Except these glass shards are propelled horizontally at speeds faster than bullets. Droplets of molten glass, carried by winds moving faster than any jet aircraft ever built, slice through the air like microscopic shrapnel. Any unprotected surface would be sandblasted and cut to ribbons in seconds. A planet-wide storm of liquid glass shards that would cut through steel. The planet's weather extremes extend beyond glass rain. Recent research led by astrophysicist Dr. Guangwei Fu at Johns Hopkins University revealed another element in HD 189733B's atmosphere: hydrogen sulfide. This is the same compound responsible for the unmistakable rotten egg smell found in sulfur springs on Earth. As Dr. Fu explained, hydrogen sulfide is a major molecule that we didn't know was there. We predicted it would be, and we know it's in Jupiter, but we hadn't really detected it outside the solar system. This discovery provides astronomers with a new method for tracking sulfur in gas planets beyond our solar system, offering insights into planetary formation and chemistry. Interestingly, the same research showed the planet's atmosphere lacks methane, which contradicted scientific expectations and demonstrates how exoplanets continue to surprise us. The combination of extreme heat, supersonic winds, molten glass precipitation, and a hydrogen sulfide atmosphere makes HD 189733B one of the most hostile worlds ever studied. Its dynamic environment creates rapid weather variations and violent storms unlike anything in our solar system. While Jupiter's Great Red Spot has raged for centuries, the storms on HD 189733B operate on a different scale entirely, with energy inputs from its star driving weather patterns of extraordinary violence. For astronomers, HD 189733B serves as a natural laboratory for extreme weather physics. By studying how atmospheres behave under such conditions, scientists gain insights that can refine models of atmospheric dynamics for other exoplanets, and potentially for Earth as well. The basic physics governing fluid movement, heat transfer, and chemical interactions remain the same throughout the universe. They're just operating under vastly different conditions on HD 189733B. What makes HD 189733B particularly valuable for research is its relative proximity to Earth. At 64 light-years away, it's practically in our cosmic backyard. This proximity allows scientists to gather data that would be impossible for more distant worlds, making this deadly blue planet one of the most thoroughly studied exoplanets. The planet challenges our assumptions about habitable environments. While HD 189733B itself is certainly hostile to life as we know it, its study helps refine our understanding of how planets interact with their stars and develop their atmospheres. This knowledge proves crucial in the search for worlds that might support life elsewhere in the galaxy. HD 189733B represents another form of cosmic rebellion, a world defying our expectations with its beautiful yet deadly nature. Many hot Jupiters share similar characteristics, but HD 189733B stands out with its blue appearance and particularly violent weather patterns. The planet's ongoing study exemplifies modern astronomy's capabilities, transforming theoretical possibilities into observable realities. As our instruments improve and observational techniques advance, we'll continue learning more about HD 189733B and worlds like it. Future telescopes may detect more trace gases in its atmosphere, map its weather patterns in greater detail, or even directly image its swirling storms. Each new piece of data helps complete our picture of this hostile, 26b, fascinating the 12.7 billion-year-old Methuselah. Beyond the violent storms of HD 189733b lies a cosmic time capsule that challenges everything astronomers thought they knew about when planets could form. What if I told you there's a planet that's been orbiting not one, but two dead stars since the universe was just 1 billion years old? Its discovery forced scientists to completely rethink the timeline of planetary evolution in our cosmos. Meet PSRB 1620-26b, affectionately nicknamed Methuselah, after the biblical figure who supposedly lived for 969 years. This cosmic Methuselah makes that lifespan look like the blink of an eye. At approximately 12.7 billion years old, this ancient world has been silently orbiting through space since long before a solar system, our planet, or even our sun existed. Earth is about 4.5 billion years old, making Methuselah nearly 3 times our planet's age, forming when the universe itself was just entering its cosmic adolescence. What makes Methuselah truly extraordinary is the peculiar system it calls home. Methuselah circles a bizarre binary pair consisting of 2 stellar corpses. The primary object, PSRB 1620-26a, is a pulsar, a rapidly spinning neutron star that emits consistent radio pulses with clock-like precision. Its companion, WDB 1620-26, is a white dwarf, the compact remnant of a star that exhausted its nuclear fuel billions of years ago. Finding a planet around this pair of dead stars required serious astronomical detective work. The planet was detected through the pulsar timing method, a technique that exploits the extraordinary regularity of pulsar radio emissions. Pulsars rotate with such consistency that they rival atomic clocks in precision. When a planet orbits a pulsar, its gravitational influence causes subtle shifts in the arrival times of these radio pulses, sometimes arriving slightly earlier, sometimes slightly later than expected. These minuscule timing deviations revealed Methuselah's presence and allowed astronomers to calculate its characteristics. The planet follows a wide orbit around both stars at approximately 23 astronomical units, comparable to Uranus's distance from our Sun. This vast orbit means Methuselah takes about a century to complete a single trip around its unusual host stars, putting it safely away from the potentially destructive forces near these stellar remnants. Methuselah resides within the globular cluster M4, a densely packed collection of ancient stars situated about 5,600 light-years from Earth in the constellation Scorpius. Globular clusters represent some of the oldest structures in our universe, with M4 estimated to be approximately 12.7 billion years old. This cluster age measurement, determined by studying the evolution patterns of its stars, provides strong evidence for Methuselah's advanced age, since planets typically form concurrently with their host stars. The cosmological context makes this discovery revolutionary. When Methuselah formed, the universe contained barely a fraction of the heavy elements that scientists once believed were essential ingredients for planet formation. In the early universe, stars had only begun the process of nuclear fusion that creates elements heavier than hydrogen and helium. These heavier elements, carbon, oxygen, silicon, iron, are the building blocks of rocky planets and the cores of gas giants in our solar system. According to conventional planetary formation theories, the early universe shouldn't have contained enough of these heavy elements to form planets. Yet Methuselah exists, proving these theories incomplete. Somehow, in conditions thought too element poor for planet formation, nature found a way. This cosmic survivor forces astronomers to reconsider fundamental assumptions about the minimum requirements for planets to form. With a mass approximately 2.6 times that of Jupiter, Methuselah is likely a gas giant without a solid surface. While we can't directly observe its composition or structure, researchers can infer its nature from its mass and the understanding of similar planets. Being located in a globular cluster adds another layer of intrigue, as these environments are known for their frequent stellar encounters that can disrupt planetary systems. Methuselah's survival through billions of years in such a dynamic stellar neighborhood speaks to the remarkable resilience of planetary systems. The formation history of this unusual system likely involves a complex dance of stellar evolution and gravitational interactions. Astronomers believe the planet originally orbited the star that eventually became the white dwarf. Later, this star-planet system was gravitationally captured by the neutron star, creating the triple system we observe today. This scenario represents a cosmic game of planetary pinball played out over billions of years. At an estimated temperature of around 72 Kelvin, minus 201 degrees Celsius or minus 330 degrees Fahrenheit, Methuselah is an exceptionally cold world, far too frigid for liquid water or any Earth-like biology. But its scientific value isn't in its habitability. Its importance lies in how dramatically it expands our understanding of when and where planets can form in our universe. By pushing the timeline of planet formation back to nearly the beginning of cosmic history, Methuselah suggests that planets, and potentially habitable worlds, might exist in places we never thought to look before. If planets could form in the element-poor early universe, they might be far more common and widespread than previously estimated. Methuselah stands as a silent witness to cosmic history, a time capsule from the universe's youth. This ancient world has observed nearly the entire history of our universe, forming before the Milky Way had fully assembled, before our sun ignited, before Earth coalesced from the solar nebula. While we often think of Earth as ancient, Methuselah has orbited its bizarre binary system for nearly 3 times longer than Earth has existed, putting humanity's brief cosmic moment in stark perspective. Trace 2b, darker than coal. Imagine a world where night isn't just dark, it's the absence of light itself. In the vastness of space, 750 light-years from Earth, orbits a planet so black it consumes virtually all light that touches it. This isn't science fiction. It's Trace 2b, a world so uniquely dark it forces astronomers to reconsider what we thought we knew about planetary appearances. What secrets might a planet that absorbs nearly all light reveal about the extremes of atmospheric science? The answer lies in Trace 2b's extraordinarily low albedo, the measure of how much light a celestial body reflects, of less than 1%. This makes it darker than any planet in our solar system and darker than most substances we encounter daily. Fresh asphalt reflects about 4% of light, while black acrylic paint reflects around 5%. Trace 2b makes these materials look positively reflective by comparison. This profound darkness stems from its unusual atmospheric composition. Unlike Jupiter's bright, ammonia-rich clouds that bounce over half of incoming sunlight back into space, Trace 2b's atmosphere is dominated by light-trapping gases, including sodium, potassium, and possibly titanium oxide. These elements function as cosmic light sponges, absorbing photons across the spectrum and converting that energy to heat. The absence of reflective cloud layers compounds this effect. Where other gas giants develop bright, light-scattering cloud bands at certain temperatures and pressures, Trace 2b's atmospheric conditions prevent such cloud formation. This combination of light-absorbing gases and cloudless skies creates the perfect conditions for an almost perfectly black planet. Discovering and measuring such darkness presented extraordinary challenges. The Kepler Space Telescope detected minuscule variations in brightness as Trace 2b orbited its star. These changes were astonishingly small, with brightness shifts as tiny as 6 parts per million, comparable to detecting the dimming caused by a fruit fly passing in front of a car headlight several miles away. Through meticulous analysis of these subtle light curves, scientists determined that the planet's western hemisphere might be marginally brighter than its eastern side, though both are remarkably dark. This slight asymmetry provides clues about potential atmospheric circulation patterns and temperature differentials across the planet's face. Despite absorbing over 99% of starlight, Trace 2b isn't completely invisible. The extreme heat, approximately 1,100 degrees Celsius, 2,000 degrees Fahrenheit, causes the planet to emit a faint, eerie reddish glow, like the dying embers of a cosmic fire. This smoldering illumination permeates the darkness, creating a world that seems to both consume light and reluctantly release it. This thermal emission accounts for approximately 95% of the light coming from trace 2b. While invisible to the naked eye at its distant location, if you could somehow transport this planet to orbit our sun at Mercury's distance, its dim red glow would be faintly visible to the human eye against the blackness of space, a smoldering cosmic ember. The contrast between trace 2b and Jupiter is striking. Though both are gas giants of comparable size, Jupiter's bright cloud bands reflect 52% of incoming sunlight, giving it the familiar striped appearance we recognize. If Jupiter were somehow coated with the same light-absorbing materials as trace 2b, it would appear as a black disk against the stars, with perhaps just a hint of its characteristic bands visible. The discovery of trace 2b challenges fundamental assumptions about gas giant planets. Scientists had long believed that planets of this mass and composition would necessarily develop reflective cloud layers as they formed and cooled. Trace 2b demonstrates that planetary atmospheres can evolve in far more diverse ways than previously imagined. This dark world serves as a valuable atmospheric laboratory. By studying how this planet's unusual mix of gases interacts with starlight, researchers can refine models predicting atmospheric behavior under extreme conditions. This knowledge improves our understanding of exotic worlds like trace 2b and potentially of atmospheres throughout the galaxy, including those on potentially habitable planets. The best fit model for trace 2b suggests an albedo potentially as low as 0.04%, effectively a cosmic black hole for visible light. The precision required to measure such values pushed the limits of Kepler's instrumentation, demonstrating how far astronomical detection capabilities have advanced. From a hypothetical spacecraft, trace 2b would appear as an almost perfectly black sphere, visible primarily by how it blocks background stars. As you approached, the faint red glow would become more apparent, giving the planet an ominous appearance, like a cosmic furnace radiating the heat of absorbed starlight. If we could somehow survive on a moon orbiting this dark giant, the view would be spectacular. The massive black disk would dominate the sky, its edges defined only by the absence of stars. During transit across its star, trace 2b would appear as the blackest of black silhouettes, a hole punched through the fabric of space itself. The extreme darkness of trace 2b reminds us of the diversity of worlds populating our galaxy. For every Earth-like planet we might discover, there exist dozens of bizarre worlds with characteristics that stretch our understanding of planetary physics. These cosmic outliers force scientists to expand theoretical models and reconsider fundamental assumptions about how planets form and evolve. The techniques developed to study this remarkably dark world have applications beyond astronomy. The ability to detect such minute light variations translates to improved capabilities in fields ranging from medical imaging to environmental monitoring. As our understanding of trace 2b continues to evolve with new observations and improved models, this dark world serves as a humbling reminder of how much remains unknown about the universe. Every exoplanet discovery introduces new questions and challenges established theories, highlighting the dynamic nature of astronomy as a field of constant discovery. Kourou 7b, the lava ocean world. While darkness consumes trace 2b, elsewhere in our cosmic neighborhood exists a world of blinding heat and molten landscapes. Meet Kourou 7b, where standing on the surface would mean your feet are literally melting into the ground beneath you. This world, confirmed in 2009 through the European-led Kourou space mission, marked a historic milestone as astronomy's first definitively rocky exoplanet, residing 489 light-years away in the constellation Monoceros. Kourou 7b orbits at an extreme distance of just 0.017 astronomical units from its star. 23 times closer than Mercury is to our Sun. This super-Earth completes a revolution in a mere 20.5 hours, creating conditions that redefine our understanding of what a rocky planet can endure. This proximity has transformed Corot, 7b, through tidal locking, with one hemisphere perpetually facing the scorching stellar furnace while the other remains in eternal darkness. This cosmic arrangement creates perhaps the most dramatic environmental contrast on any known planet. The star-facing hemisphere exists in a perpetual inferno. Temperatures across this eternal day side range between 1,000 and 1,500 degrees Celsius, hot enough to transform ordinary rock into vast rivers and oceans of molten lava that flow across the landscape. Silicon, iron, and other elements that form solid ground on Earth exist here in liquid state, creating a hellscape beyond imagination. Meanwhile, the night side experiences permanent darkness without direct starlight. The temperature differential between hemispheres drives perhaps the most bizarre weather cycle in the known universe. As rock vaporizes on the day side, silicate vapors form a tenuous atmosphere that flows toward the cooler night hemisphere. There, something remarkable happens. The vaporized rock condenses and precipitates back to the surface as droplets of molten stone. Imagine standing on the twilight boundary between hemispheres, watching the horizon glow with orange-red light as globs of liquefied rock fall like fiery teardrops, sizzling and merging with the landscape upon impact, releasing plumes of metallic steam that rise into the alien sky. This rock cycle operates on the same principles as Earth's water cycle, but with materials that remain solid on our planet. While we experience rain and snow, Corot, 7b experiences downpours of liquid rock, transforming our Earth-centric understanding of planetary processes. Corot, 7b falls into the classification of super-Earth, though this term can be misleading. While technically referring to planets larger than Earth but smaller than Neptune, Corot, 7b shares little with our comfortable blue marble beyond its rocky composition. Measurements indicate it has about 1.58 times Earth's radius and approximately 6 times Earth's mass, yielding a density of about 5.2 grams per cubic centimeter, comparable to Earth's makeup and confirming its predominantly rocky nature. This combination of size and mass means that if you could somehow stand on its surface, ignoring the impossible heat, you'd experience gravity significantly stronger than Earth's. Every movement would require considerably more effort, and objects would feel substantially heavier, assuming they hadn't already melted into the landscape. The planet's discovery represents a triumph of modern astronomical techniques. The Corot Space Telescope detected this world through the transit method, observing minute dips in starlight as the planet crossed in front of its host star. The signal was incredibly faint. The periodic transits lasted just 1.3 hours with a light diminution of only 3.4 times 10⁻⁴, or about 0.034%. After collecting 40 days of data, the mission's pipeline algorithm detected this shallow signal, triggering follow-up observations from ground-based telescopes to confirm the planetary nature of the object. The finding was formally announced on February 3, 2009, during the Corot Symposium in Paris, and later published in a dedicated issue of the journal Astronomy and Astrophysics. Corot, 7b's significance extends beyond its extreme conditions to what it reveals about planetary diversity. Before exoplanet discoveries began in earnest, astronomers based their understanding of planetary systems largely on our solar system's architecture. Corot, 7b reveals an entirely different class of worlds. Rocky planets orbiting incredibly close to their stars, experiencing conditions with no analog in our home system. These lava worlds force us to reconsider fundamental assumptions about planetary formation and evolution. Their existence raises questions. Did they form in their current locations, or did they migrate inward? How do they retain any solid material under such extreme heating? The answers continue to reshape theoretical models. Corot, 7b bridges astronomy and geology. Understanding its surface requires knowledge of how rocks behave at extreme temperatures and pressures. The planet functions as a natural laboratory for studying states of matter under conditions impossible to replicate on Earth. As the first confirmed rocky exoplanet where both mass and radius could be measured with sufficient precision to determine its composition, Corot, 7b opened the door to exogeology, the study of geology beyond our solar system. Despite being uninhabitable by any conceivable standard, Corot, 7b offers valuable insights into planetary science. Its study contributes to our understanding of how worlds form and evolve under extreme conditions, potentially informing models of early Earth when our planet was largely molten. It also helps define the inner edge of habitable zones around stars, showing us where conditions become too extreme even for the most robust forms of theoretical life. J1407b, the Super-Saturn with colossal rings. While Corot, 7b pushes the limits of what rocky means with its molten landscapes, our cosmic journey now takes us to a world that rebels in an entirely different way, through sheer spectacular adornment. In the constellation Centaurus, 434 light-years from Earth, astronomers have discovered what might be the most dramatic planetary accessory in the known universe, the ring system of J1407b. If you've ever marveled at Saturn's rings through a telescope, prepare to recalibrate your sense of wonder. J1407b's ring system spans a diameter of 180 million kilometers. That's approximately the distance from Earth to beyond Venus. To put this in perspective, if we somehow transplanted J1407b to Saturn's position, its rings would dominate our night sky, visible to the naked eye as a massive celestial structure dwarfing our moon in apparent size. The discovery of this extraordinary system came in 2012, when astronomer Eric Mamajek was analyzing data from the SuperWASP project. At first, it appeared as a peculiar anomaly, something unusual that didn't quite fit established patterns. The parent star, J1407, had exhibited a strange dimming behavior over a 2-month period in 2007. Most transit events dim a star's light by around 1%, but J1407's brightness plummeted by a staggering 95% at certain points. This dramatic light reduction pointed to something massive passing between the star and our telescopes. As astronomers investigated further, the patterns of light variation revealed themselves like a cosmic fingerprint, an intricate ring structure with remarkable detail. Each rapid change in the light curve, occurring within mere tens of minutes, mapped out what appeared to be thousands of individual rings, a cascading waterfall of cosmic debris encircling a massive world. What makes this system extraordinary is its complexity. The rings are structured into more than 30 distinct bands with varying densities and compositions, resembling a cosmic version of tree rings, each band telling a part of J1407b's evolutionary history. The total material contained within these rings amounts to approximately 1 Earth's worth of matter, substantially more material than Saturn's comparatively delicate ring system. Perhaps most fascinating are the gaps between certain rings. These aren't empty spaces, but rather clearings created by moon formation. One particularly prominent gap suggests the presence of an exomoon in the making, potentially containing 80% of our moon's mass. If confirmed, this would be larger than any moon in our solar system and would give us front-row seats to moon formation in action. The central object itself, J1407b, remains somewhat mysterious. With a mass estimated at 20 times that of Saturn, it sits at the boundary between what we'd classify as a planet and what astronomers call a brown dwarf, essentially a failed star that never accumulated enough mass to ignite nuclear fusion in its core. This massive size contributes to its ability to hold such an expansive ring system in its gravitational influence. The young age of the system, the star J1407, is only about 16 million years old, suggests we're witnessing something transitional. The rings resemble a cosmic snow globe, temporarily suspended in a pattern we can observe before it settles into something new. The sheer mass of material provides enough resources to form multiple moon-sized objects over time. Computer simulations offer intriguing insights into how such an enormous ring system maintains stability. If the rings orbit in the same direction as the planet, prograde, the star's gravity would likely tear them apart. However, if they orbit retrograde, opposite to the planet's motion, they would remain more stable, as the particles never stay close enough to the star for long enough to experience significant disruption. The star itself, J1407, contributes to this cosmic spectacle. It's a young, sun-like star with a remarkably rapid rotation period of just 3.2 days. This fast rotation is characteristic of young stars that haven't yet slowed down through the process of magnetic braking that our sun has experienced over billions of years. The interaction between this energetic young star and its massive planetary companion creates a dynamic system constantly evolving before our eyes. Studying J1407b's ring system offers astronomers an unprecedented opportunity to witness moon formation in real time, a process that shaped our own solar system but occurred billions of years in our past. As particles collide and coalesce within the rings, they gradually build larger structures, the very beginning stages of moon formation. What's particularly valuable about J1407b is that it provides a test case for our theories of how planetary systems evolve. The process we're observing mirrors what likely happened around our early sun, as gas and dust in the protoplanetary disk gradually clumped together to form the planets we know today. The discovery of J1407b represents a triumph of modern astronomical techniques. The extreme nature of its transit signal, with complex patterns and deep dimming, stands out dramatically even among thousands of exoplanet discoveries. For all we've learned about J1407b, many questions remain. How long will these magnificent rings persist? Are we catching them at a special moment in their evolution? Or do such massive ring systems commonly exist around young giant planets? Could similar structures exist elsewhere in our galaxy, waiting to be discovered? And what will become of the moons forming within these rings? These questions drive astronomers to continue monitoring J1407b, hoping to catch another transit event that would provide updated information on how the system is evolving. Each observation adds another piece to this cosmic puzzle, helping us understand the broader processes of planetary formation revolution throughout the universe. The universe doesn't just contain J1407b's spectacular rings. It's filled with planets that shouldn't exist according to the textbooks written before the exoplanet revolution. From worlds being actively torn apart by their stars to planets older than most stars, these cosmic outlaws are forcing us to create entirely new rules of planetary formation. Just 15 years ago, astronomers had a relatively simple view of how planetary systems formed. The model was largely based on our own solar system. Rocky planets near the star, gas giants farther out, with relatively circular orbits and predictable compositions. It was a neat, orderly theory that seemed logical until we started discovering actual exoplanets. Each of the 7 extraordinary worlds we've explored represents a fundamental challenge to this conventional understanding. These are radical departures that demand entirely new explanations. The neat, orderly universe of our textbooks has given way to something far more chaotic, creative, and fascinating. Consider TOI 849b, the exposed planetary core. Its existence suggests that gas giants don't always follow the expected developmental path. The prevailing theory held that once a rocky core reached sufficient mass, it would inevitably accumulate and maintain a massive gaseous envelope. TOI 849b stands as living proof this isn't always the case. Whether through catastrophic collisions, atmospheric stripping by its star, or a failure in the initial formation process, this planet demonstrates that planetary evolution can take unexpected turns. TOI 849b gives astronomers unprecedented access to study something they could previously only theorize about: the internal composition of gas giant cores. By analyzing the spectra of light passing through what little atmosphere remains, scientists can directly measure the elemental abundance within this exposed core, providing crucial data to refine models of planetary interiors. J1407b's enormous ring system carries equally profound implications. The traditional view of moon formation around gas giants was largely theoretical, pieced together from studying the end results in our solar system. But J1407b offers a chance to witness this process in action. The fine structures within its rings, particularly the gaps that indicate emerging moons, provide a real-time laboratory for studying satellite formation. The scale of these rings, containing an Earth's worth of material, suggests that moon formation can be far more dramatic than previously understood. The tens of minutes changes in the light curve revealed incredibly intricate structures that challenge our comprehension of how such massive ring systems remain stable. WASP-12b and HD 189733b showcase the remarkable resilience of planets in extreme environments. The conventional wisdom once held that planets extremely close to their stars would be rare, as such hostile conditions would prevent formation or ensure quick destruction. Yet these worlds exist and exhibit complex atmospheric compositions. WASP-12b's active destruction and HD 189733b's exotic weather systems demonstrate that planets can persist in conditions far more extreme than once thought possible. These discoveries push the boundaries of what we consider possible environments for planetary bodies. If planets can survive glass rain and intense stellar radiation, what other seemingly hostile environments might harbor worlds yet undiscovered? Each observation of these extreme planets refines our understanding of atmospheric physics under conditions impossible to replicate in Earth laboratories. Methuselah, PSR B1620-26b, challenges our most fundamental assumption about planetary formation, when in cosmic history it became possible. The conventional view held that planets required heavy elements that could only be produced after multiple generations of stars had lived and died. Methuselah's age forces us to reconsider this timeline entirely. If planets formed nearly 13 billion years ago when the universe contained fewer heavy elements, then the timeline for planetary evolution, and potentially life, extends much further back in cosmic history than previously thought. This discovery expands the search window for potentially habitable worlds and suggests that planetary formation has occurred for nearly the entire history of the universe. Trace, 2b, and Corot, 7b highlight the extraordinary diversity in planetary compositions. The differences between these worlds, one an ultra-dark gas giant absorbing nearly all light, the other a scorching super-Earth potentially covered in lava oceans, demonstrate that planets can form with a far wider range of compositions than our solar system suggested. These discoveries require astronomers to develop models accounting for planets with atmospheres containing light-absorbing chemicals like those on Trace, 2b, or worlds with extreme temperature gradients where rock becomes part of the weather cycle as on Corot, 7b. The combined impact of these discoveries has triggered a revolution in our understanding of planetary formation. Scientists have developed new models that account for the incredible variety we're finding, from hot Jupiters to super-Earths, from exposed cores to worlds with exotic compositions. These theories explain how planets migrate from their formation locations, how atmospheres can be gained or lost, and how planetary systems develop in configurations radically different from our own. What's emerging is a picture of planetary formation as a dynamic, varied, and complex process. These discoveries have fundamentally altered our approach to searching for planets. Rather than looking for solar systems resembling our own, astronomers cast a wider net, recognizing that planets form and survive in environments once thought impossible. This expanded search has led to thousands of additional exoplanet discoveries, The implications extend beyond planetary science. Our understanding of star-planet interactions, atmospheric evolution, and system stability has been transformed. Questions once considered settled have been reopened, and new research avenues have emerged. Graduate students now study multiple competing theories, each with strengths and limitations. This scientific revolution reminds us of a fundamental truth. The universe consistently outpaces our imagination. For every rule we establish, nature shows us an exception. As we've seen with these 7 remarkable worlds, the cosmos harbors realities far stranger and more wonderful than our limited human minds initially conceived. Redefining habitability. Nature's determination to surprise us extends beyond planetary physics into perhaps the most profound question of all. Are we alone? The extreme conditions on these rebel worlds force us to confront an uncomfortable possibility that in limiting our search for life to Earth-like conditions, we might be overlooking countless alien biospheres hiding in plain sight. For decades, astronomers focused their search for extraterrestrial life within a narrowly defined Goldilocks zone, that special orbital region where a planet could maintain liquid water on its surface. Earth harbors life and has liquid water, so this approach seemed logical. But as our planetary catalog has expanded to include worlds with glass rain, lava oceans, and exposed cores, are we trapped in a tunnel of possibilities, viewing the universe through an Earth-centric lens that blinds us to other forms of life? The discovery of these cosmic rebels has forced astrobiologists to recalibrate their entire approach to searching for life beyond Earth. Each impossible planet serves as a reminder that the universe has far more imagination than we do. If planets can exist in configurations we once thought impossible, perhaps life, too, can arise and thrive in environments we'd previously dismissed as utterly inhospitable. The broader approach to habitability dramatically expands the potential real estate for life in any given solar system. Consider the enormous ring system surrounding J1407b. Within those complex bands of material, containing roughly an Earth's worth of matter, scientists have detected gaps suggesting the presence of forming moons. These exomoons, developing within this dynamic environment, could potentially harbor conditions suitable for life, not on their surfaces but beneath them, much like Jupiter's moon Europa or Saturn's Enceladus in our own solar system. These moons might maintain vast subsurface oceans kept liquid by the gravitational tug-of-war between the planet and its parent star. These hidden oceans would be shielded from radiation by thick ice crusts while still receiving the heat necessary for liquid water. The tidal forces exerted by gas giants like J1407b could generate enough internal heat to maintain these subsurface oceans for billions of years, potentially long enough for life to emerge. This possibility expands our understanding of where life might exist, as gas giants like J1407b appear to be relatively common throughout the cosmos. Even planets that seem decidedly hostile might have more to offer than we initially recognize. Worlds like HD 189773b, with its sideways glass rain and extreme winds, demonstrate that planetary systems can produce remarkably diverse environments. While the planet itself might be utterly inhospitable, its existence points to the diversity of worlds that might orbit the same star. For every scorching hot Jupiter we detect close to a star, could temperate, rocky worlds orbit at greater distances, invisible to our current detection methods. The ancient planet Methuselah pushes our thinking in an entirely different direction, chronological rather than environmental. If planets could form when the universe was just 1 billion years old, then life may have had the opportunity to emerge and evolve for nearly 13 billion years in some parts of the cosmos. This timeframe dwarfs Earth's 4.5 billion-year history and the roughly 3.7 billion years that life has existed here. What forms might life take given 3 times longer to evolve than terrestrial organisms have had? Methuselah's existence extends the timeline for possible biological evolution far beyond what we'd previously imagined. Even a planet with conditions as extreme as TOI 849b, an exposed planetary core subjected to incredible heat and pressure, expands our thinking about planetary evolution. If gas giants can lose their atmospheres or fail to fully form, then the development of potentially habitable worlds might follow similarly unexpected pathways. Could worlds that begin their lives as gas giants transform into terrestrial planets with conditions suitable for life? A planetary evolution path entirely unknown in our solar system, but potentially common elsewhere? The James Webb Space Telescope represents humanity's most powerful tool yet for investigating these possibilities. With its unprecedented ability to analyze the chemical composition of exoplanet atmospheres, JWST can detect potential biosignatures, gases that might indicate the presence of life. Astronomers are now casting a much wider net, examining the atmospheres of diverse worlds, including those that orbit in configurations once thought impossible. One particularly exciting frontier in this expanded search involves exomoons orbiting massive planets in binary star systems. While no specific exomoon has been definitively confirmed yet, the presence of objects like Methuselah, which orbits a binary system consisting of a pulsar and a white dwarf, demonstrates that planets can form and persist in complex gravitational environments. If planets can exist in such systems, moons likely can too, potentially offering stable environments where life could emerge. This broader approach acknowledges that our single example of a life-bearing world, Earth, might represent just one possibility among many. Life on Earth evolved under specific conditions, but there's no reason to assume those conditions represent the only pathway to biological complexity. The chemistry that underlies terrestrial life might function in environments drastically different from Earth's surface, or alternative biochemistries might exist altogether. Even Trace 2b, the darkest world known, prompts questions about unconventional habitability. Its near-complete absorption of light means its thermal profile differs markedly from anything in our solar system. While the planet itself is unlikely to harbor life as we understand it, its existence demonstrates that planetary characteristics can vary far more widely than we once imagined. Could habitable conditions arise in equally unexpected configurations? We now recognize that potentially habitable environments might exist in places we never thought to look. In subsurface oceans of distant moons, on rogue planets drifting between stars, in the clouds of Venus-like worlds, or in the atmospheres of gas giants. By breaking free from our Earth-centric definition of habitability, astronomers have dramatically expanded the search for extraterrestrial life. As we've explored these 7 extraordinary planets that defy conventional understanding, we're witnessing just the beginning of a cosmic revelation. With more than 5,630 confirmed exoplanets already cataloged, our journey of discovery is accelerating, not concluding. The James Webb Space Telescope and Habitable Worlds Observatory will analyze alien atmospheres with unprecedented detail, transforming our understanding of what's possible. These missions invite you to join humanity's greatest adventure, uncovering worlds stranger than fiction. What undiscovered planets might circle the stars you see tonight? Each point of light may harbor revelations that challenge everything we know about our vast, boundlessly creative universe.